Okay, thank you, Daniel. So can everyone see my screen? Um, okay, thanks. I think there has been a very interesting topic going on in our school. I'm not sure about other institutions, but we realized that every method of theory class that we took, the ethics section is almost at the very end of the class. So I guess, ethics are a very important topic. And I think when we're playing with tools, we have to read the manual properly before doing that. Okay, so I'm going to continue to discuss ethical issues and bias in AI. So as we learned from class, machine learning and AI models that could process a lot of different forms of data, like topic, tabular data, textual data, and as we just learned, image data. And they're all very powerful. So in this class, we have hands-on experience of building those models, which is fantastic. And in 2018, the very famous NLP competition called SemEval, they released a competition of predicting sentiment in tweets. And they provide several tasks for the SEM dataset. So this task I'm showing here is a multi-label classification task, which means that for the same tweets, it could have like several different labels at the same time. For example, for this sentence is both anger and disgust at the same time. So those are all the top submissions. As we can see, those models, some of them are based on deep learning based methods, and some of them are based on more conventional methods such as SVM and random forest. And they all achieved relatively good performance in 2018. And instead of relying on only the validation or test split, the SemEval committee, the organizer behind the competition, developed another validation set called Equity Evaluation Corpus. We can call it EEC here. So they propose templates you can replace names and emotion words, and those names you can invert gender or ethnicity information, and the emotion word here, by replacing those words, you can infer the general sentiment in the entire sentence. And the dataset have a few thousand data points, and the competition committee can use all the submissions to do prediction on the EEC dataset. The result shows that for a lot of the classifiers, they have gender bias. So in some sentiment classes, male have a higher score compared with female, even though the emotion words are the same in the template. So the application of machine learning are truly amazing, and we're probably using it all the time. Just think about the voice assistant that we use and Face ID or fingerprint sensors that we use every time we unlock our screens. And computer program that beats the world champion of chess many decades ago. And the highlight of AI is that they are generating memes on the internet. So even though there are countless examples of AI changing our life forever, it suffers from many flaws. One of the very relevant flaws in that is that some of those AI models might have human bias embedded. Governments have been using AI to make very important decisions, but those decisions are not always made fairly by the AI agents. According to the report, some governments have been using facial recognition models to predict whether a person is going to commit crime in the future. So examples of the model predicting shows that those systems are often have human bias related to underrepresented groups. So the sample here shows a very specific bias prediction. A white male with criminal records could be predicted as someone who has a very low risk of committing crime in the future. Likely because the system is making prediction using the face of a white man, while on the other hand, a black woman with very few criminal records were predicted as someone with a high risk to commit crime again. To give another example, Vision AI is a service provided by AI. They provide the service to, for example, small businesses, though the small business don't have to build their own machine learning models to do image recognition. It's powered by computer vision, which is a very successful and popular application of machine learning and deep learning. And last year, I think maybe 2 years ago in 2020, human bias has been discovered in those image recognition model. So even though the company claims that the model has very high accuracy, it tends to make decisions with human bias. So in this example, the model tends to predict that a hand with a darker tone is holding a gun, and a hand with a lighter tone is holding a monocular. To give another example, a face recognition software powered by machine learning was found to have a hard time figuring out whether an Asian man has their eyes closed or not. Regardless of how powerful AI is when it actually works, having human bias embedded in those models could bring actual harm. So to list a few, quality of service harm will be done when a system does not work as well for one person as it does for another, or as well for one group of people as it does for another group of people. So to give a very concrete example, remember how the facial recognition software thinks the man has his eyes closed. It might be less possible to reduce those errors when the man is white. Allocation harm will be done when AI-based system extends or withholds opportunities, resources, or information. A very concrete example is, for example, a mortgage application or job application system that is automated with machine learning or AI. So to explain why machine learning and AI models might be biased, we need to go back to the steps and process that we take to build those models. So to build a machine learning model with predictive power, we'll first need to human label dataset. So by minimizing the prediction error by constantly updating the model, we will eventually get a model that knows the patterns in the training dataset very well. And by evaluating model performance on verification split, we test how well the model might work in the real world and measure the generalized error. And if it finally achieves a very good performance on the verification split, we will use it in real world tasks like the application that's currently running in our phones, computers, tablets. But in this summer school, we are only looking at the training and validation steps, but there are a few steps before and after model training process. First of all, for supervised learning tests, it's totally impossible to train a model without training data. And those data are painstakingly collected and curated by a human. After training the model, during the model application process, we need to interpret those models to get more knowledge about the test. Like we did earlier for the citation worthiness test, we are looking at what are the most important tokens for the classification test in order to figure out what we need to adjust in order to build a better model for the task. And a proper interpretation could be checking feature importance like mentioned. And with the application and interpretation of the model, we will have a better understanding of the problem we are trying to deal with. And what we learn from the entire training and interpretation process will affect how we collect, annotate, and curate data sets. And during the annotation process, annotators who have painstakingly labeled data for model training could come from different backgrounds. They might have different gender or ethnicities. Each of them will look at the world differently and have different opinions about incidents. It's possible that the dataset inherit annotated bias. In the final product of the annotation process could be bias label in that case. And for the data collection process, researchers might take a random sample for model training, but sometimes the data selection process might also include biases. And in a dataset about scientists in the field, in the data collection process, the data curator might be only looking at scientists in the Western world, and for example, in America or in Europe, since the curator don't know a lot about Chinese language, Indian language, or Japanese language. So scientists outside of America and Europe will be missed out from the dataset and thus being underrepresented. When we want to train a model, we usually want the training dataset to be a real random sample. So the dataset is a vivid representation of the real population. So when we do the validation, it's actually calculating the real generalization error. And the dataset itself might also include human bias. To give an example, there are machine learning models for text mining tasks. Some of the models are based on word co-occurrence, such as word embedding. And the co-occurrence of words in historical literature might pass the human bias onto the model. If in the historical literature there are more female nurses than male nurses, the model might tend to believe that a nurse is more likely to be female. After we have a model that performs relatively well on the validation split, in order to better understand the prediction task, we usually try to interpret the model. In that process, confirmation bias over generalization and correlation fallacy might be introduced to the loop of creating those models. When researchers or engineers are interpreting the model, the process might be influenced by their personal preference or pre-existing belief or hypothesis. So we, as researchers, we all tend to pick a little bit. On top of that, there might not be enough information for researchers to draw any conclusions. Maybe when the researchers are trying to use, for example, an image of a face to predict whether a person is good at math, a face. So for that specific task, a face has too little information for the test, and the information could be wrong or totally irrelevant to the task. So if they eventually come to the conclusion based on partial interpretation of the model, they might come to a conclusion that is also partially correct. A very common mistake is correlation fallacy, in which cases humans infer causal relationship from the interpretation, while only correlational relationships are presented. So human bias are present in multiple stages in the model building iteration. So in the loop, human biases will accumulate if we ignore those phenomena in each stages. Even though we might be well aware of the biases hidden in machine learning and AI models, it is still challenging for us to understand how exactly what machine learning models make a biased decision. So in the previous section, as Danny mentioned, so on Tuesday, we have just discussed models that are less complicated, such as logistic regression. It is relatively easy to make interpretations since those each feature of a data point is directly related to a coefficient moving part inside the model. So for those relatively easy models, it's relatively easy for us to figure out the inner decision-making mechanism in the model. But when you compare logistic regression with a very, very simple neural network, is basically several logistic regression stacked together. So even in this very simple example, we can't really have a clue about which part of the model accounts for which feature. So as Daniel mentioned, in many cases, we will deal with hundreds, if not thousands of coefficients. So it means that it will be even more challenging to figure out how the model is making a decision. This visualization shows the relationship between accuracy and interpretability. Typically, more complex models, such as deep learning models, could fit a more complicated curve. So it's more likely they will do a better job at prediction. But they usually have weaker interpretability. So the purpose of this section is not to scare you off so that you will never use machine learning models anymore. So given what we have painstakingly studies about how to build machine learning models ourselves. So given all the setbacks, we cannot ignore the fact that all those AI applications have potential to make our life easier. With AI and machine learning, we can make better decisions, more discoveries, and help us better understand the world endlessly. So we should not throw away the baby with the bathwater. There are a handful of procedures we should do to mitigate algorithmic bias from AI and machine learning models. We should be mindful of fairness in each step of model building. In the data preparation step, we should understand the skewness and correlation in our dataset. We should be mindful of the distribution of the data. We should learn whether all subsets of our model are equally represented. For example, in a data set for a facial recognition application, is the number of white faces equal to the number of African American faces? We should acknowledge the imbalance in our dataset and do proper adjustments, such as downsampling or data augmentation, like what Han presented earlier. And for some tasks, we should remove data points that include stereotyping, sexism, and racism that might cause human bias in our model. If certain groups in the dataset are underrepresented, we should seek more data for those subgroups. In the model training step, we should do proper cross-validation so that the model we train has better generalization power, in the sense that is more likely to be good in the real world. We should also define a health outset for high use cases. For instance, define a list of test sets with only Asian researchers and see if the prediction of researcher future success also makes sense. We should also be mindful of what features we choose for model building. We should identify and remove sensitive information that is irrelevant to the prediction task. One example of mitigating human biases in classifier is using multitask adversarial training. So in this example, we have the target task we usually want to train. For example, whether researchers is going to win Nobel Prize in the future. On top of that, we add another layer on top of the hidden layer to predict gender, race, etc. So instead of minimizing the error here, we maximize the error so that the classifier, when the classifier is being trained to predict whether a researcher is going to success, it will ignore all sensitive information or race, gender for the data point. So no gender or race bias will be introduced in this process. And after training the model, we need to have a proper metrics to evaluate whether the model is fair. So in this class, we have looked at a few performance evaluation, and this is the confusion matrix, and you might be familiar with. Based on this matrix, we develop different metrics to validate the model performance, such as F1. So here we use recoil and position. Those different metrics are used in different scenarios. For example, when in a classification task for predicting whether a paper is going to be retracted or whether a journal is predatory, we need to make a very careful prediction so that we don't piss off anybody. So in that case, we need to minimize the false positive. So in that case, precision would be a better choice to evaluate the model. So, and here are two metrics that we use to make sure the performance across subgroups works equally well. And aside from performance evaluation, there are a lot of other tools that are open access and we can use to interpret more complicated models such as deep learning-based image recognition or NLP models. And is there any questions so far? Okay. So I'll continue to walk through the demo that I made to identify and detect bias in word embedding models. So the notebook could be seen under the deep learning folder. It is called bias in word embeddings. So I have run these steps so that we don't have to stare at the screen. So this package includes algorithm to detect bias in word embeddings, and it also imports the graph word embeddings, which is the state-of-the-art word representation model. So after importing, this is basically a dictionary. So we can get word embeddings by the key. And we can do a similar calculation that we just talked about. So because graph is a better word representation, you can see that the similarity between man and king is very close to the similarity between woman and queen. Meaning that there are more accurate semantic information in graph embeddings. And here we introduce bias detection method in word representation inspired by psychophysics. So in this process, we actually generate mixture of the word embeddings of nurse with woman and man. And we constantly adjust the ratio of women or men in the mixture of word embeddings. And based on cosine similarity, we take notes of the point where we cannot decide whether the mixed embedding is a woman nurse or a female nurse or a male nurse. So as it shows here, when there is almost zero women in the mixed embedding, we couldn't decide whether the mixed embedding is male or female, meaning that in most of the time, based on the word representation, the nurses are more likely to be female compared to men. And here I have a bunch of application words for applications, and I got a bunch of pairs of gendered words. And so at the point where we cannot decide whether a nurse is male or female is called point of subjective equivalent. And in this graph, each dot is a point of subjective equivalent, meaning that at which point we cannot decide whether an occupation is more likely to be male or female. So we can see that according to the word representation model, hairdressers, paralegal, therapists, nurses are more likely to be female, while technicians, plumber, physicians, lawyers, chemists, programmers are more likely to be male. And please feel free to play with this demo. And do I have any questions before I wrap up? Okay. Thank you.
Okay, thank you, Lijian. It's a very important topic, and I hope people mind more about these issues in science. Okay, so so I guess we wrap up very early. So we will. I will leave the Zoom open so that if people want to interact, and maybe Lijian, if you want, I guess I'm going to stop the recording now.